Previously, for a finite dimensional real vector space V, we have defined the notion of an almost complex structure on V. Now we want to look at a special case when V is a Euclidean vector space. That is, when V is equipped with some positive, definite, symmetric bilinear form. In that case, we want to study the relationship between the scalar product and the almost complex structure on V. But first we need a definition. So we say that an almost complex structure I is compatible with this scalar product if the following holds, i.e. if I preserves the scalar product on V. So when V is a Euclidean vector space, what is the relationship between the scalar product on V and an almost complex structure on V? It turns out that in the case of dimension 2, these two notions are almost equivalent. In higher dimension, it's gonna be a bit more complicated, but let's first discuss the case of dimension 2. If V is a Euclidean vector space of dimension 2, then we have the following bijection. We actually have a bijection between the set of scalar products on V up to conformal equivalence and the set of almost complex structures on V. What does it mean for two scalar products to be conformally equivalent? Well, let's review quickly. So let's say we have these two scalar products. Then we say that they are conformally equivalent if and only if they differ by a positive scalar. So what is this correspondence? Well, given a scalar product on V, we can define an induced almost complex structure as follows. Intuitively, we want to think of this I as counterclockwise rotation by pi over 2. Where the hell does this come from? Well, remember, this big I basically corresponds to the multiplication by I map. Now let's recall the geometric meaning of this map in the case of the complex plane. Observe that in that case, multiplication by I just corresponds to counterclockwise rotation by pi over 2. Alright, so that's good for the case when V is C, viewed as a two-dimensional vector space. But what would these terms mean in the case of a general vector space V? What would counterclockwise mean and what is pi over 2? To that end, we want to fix an orientation on V. So let's assume that it's oriented. We can capture the idea that I is rotation by pi over 2 in some fixed direction by describing it as follows. For any non-zero vector V, we should have that I of V should be orthogonal to V, and it should have the same norm as V. These two conditions captures the intuition behind rotation by pi over 2. And to say that it's in a fixed direction, we will just require that this is positively oriented. You can check that these three conditions determine a unique almost complex structure on V. And from this condition, we immediately have that I is compatible with a scalar product. And we can also see immediately that two conformally equivalent scalar products must induce the same almost complex structure. Conversely, any almost complex structure on V arises this way, so we have this bijection in the case when V is of dimension 2. Now, how about the case when V is a Euclidean vector space of arbitrary dimension? In that case, does every scalar product still uniquely determine an almost complex structure on V and vice versa? Not quite. In that case, what will happen is that on V we need to look at a triple, so the scalar product and an almost complex structure on V, but also an induced fundamental form. And then any two of these will determine the third one uniquely. So that's the topic of our next video.